Okay, we're continuing to look at problems from test review number 3. In problem number 19. So problems number 19 through 30 all seek for us to basically just use a short test. These problems do not typically involve a lot of work. But this really quickly, can you tell whether a series converges or diverges? And can you say by which test? So number 19 is the sum, as n goes from 1 to infinity, of 1 minus e raised to the power negative n. So I'm going to just rewrite this as 1 minus 1 over e to the power n. And instead of finding the sum, let's find the limit. So the limit as n goes to infinity of this expression is equal to 1 minus 0, which is equal to 1. And so since the limit does not go to 0, we can say that the series, the original sum, diverges by the divergence test. Problem number 20, we have the sum of negative 1 to the power n over n. So this is an alternating series, and I'm just going to write it in a way that the alternating component is sort of isolated, and we can very clearly see then the remaining sequence part here is 1 over n. So I'm going to use the alternating series test and check that number 1 over n is decreasing, which in fact it is. You can really quickly verify by graphing or writing out a few terms or finding the derivative of 1 over n. All right. Number 2, we will check to see that the limit as n goes to infinity of 1 over n is equal to 0. In fact, it is. So since the two properties for convergence of alternating series hold, we can state that this is in fact convergent by alternating series test. But now it's no longer enough just to state that an alternating series converges. We need to add to that statement whether this convergence is absolute or conditional. So what we're going to do is we're going to test the series without the alternating component. So if we just strip the series from its alternating component, this is the sum of 1 over n, which we see is the divergent harmonic. So therefore the original alternating series converges conditionally. Number 21, we have the sum of 1 over the square root of n. All right, so we could write this as the sum of 1 over n raised to the power 1/2. And so if we compare this to a p-series, this is a p-series, we will see that this is divergent. Since my value for p is greater or equal to 1, this series diverges by the p-series test. Number 22. We have the sum of 2n plus 4n squared divided by 2n squared. Again, here I'm going to use the divergence test, so I will check the limit of the sequence. The limit as n goes to infinity of 2n plus 4n squared divided by 2n squared. Again, since the degree of the top and the bottom are the same, this limit goes to the ratio of the leading coefficients, 4 over 2, which is equal to 2. The limit does not go to 0, therefore this series diverges by the divergence test. Number 23, we have the sum as n goes from 1 to infinity of n factorial divided by 8 to the power n. So we said that anytime you deal with a series that has either factorials or power towers, that means n is part of the base number and part of the exponent, you're probably best off trying the ratio test first. So I will set up the limit as n goes to infinity of a sub n plus 1 divided by a sub n. So in this case, the limit as n goes to infinity of n plus 1 factorial divided by 8 raised to the power n plus 1, quantity divided by n factorial over 8 to the power n. So we don't like working with complex fractions. I'm going to flip and multiply. But also, as I flip and multiply, I'm going to just rearrange my terms so that I see like terms together. And now I'm going to make a simplification. So as far as the base 8 terms go, 8 to the power n divided by 8 to the power n plus 1. After cancellation, I'm simply left with an 8 in the denominator. And n plus 1 factorial divided by n factorial, we will have, after cancellation, simply an n plus 1 in the numerator. So now if we take this limit is equal to infinity, and so by the ratio test, this series will diverge, as our limit is strictly greater than 1. All right, problem number 24, we have the sum of n to the power -2. Again, we could write this as the sum of 1 over n to the power 2, and this series will converge by the p-series. This is a convergent p-series. Number 25, we have the sum of n to the power 4 times e to the -n to the power 5. All right, so for this problem, I'm going to use the integral test, and I'm going to start by just expressing the sequence a sub n as a function f of x. So f of x here will be x to the power 4 times e to the -x to the power 5. I'm going to check that my three conditions hold, that it is positive, decreasing, and continuous, which in fact it is. You can tell that really quickly by graphing. And so I will set up the integral going from 1 to infinity. And I'm going to properly state, since the integral is improper, I will state this as the limit as a approaches infinity of the integral going from 1 to a of x to the power 4 times e to the -x to the 5th dx. All right, so I'm going to leave the limit and the bounds aside for just a second. Let's quickly just focus on the indefinite integral here. In order to evaluate this integral, we will use u substitution, and I will let u be equal to -x to the power 5. So it follows then that du is equal to -5x to the power 4 dx. I do have an x to the power 4 dx in my original expression, so I'm just going to move the -5 to the other side of the equation. We get -1/5 du equals x to the power 4 dx. So a substitution here yields -1/5 times the integral of e to the u du. This integral is equal to -1/5 e to the u. And then back substitution gives -1/5 times e to the -x to the power 5. And even though the problem presented this with a negative exponent, I know I really don't like working with negative exponents, so I'm going to move the term e to the -x to the 5th into the denominator, and that's going to make that power positive. It's going to eliminate that negative exponent for me, which is really important if you're working with limits as infinity. All right, so back to my original problem. We have the limit as a approaches infinity of -1 over 5 times e to the x to the 5th, evaluated from 1 to a. The fundamental theorem of calculus says plug and top minus plug and bottom. And note that the coefficient -1/5, I'm just going to leave that on the outside. That is going to make my calculation just a little bit easier. All right, so if we go ahead and evaluate the limit, a is equal to infinity, we see that the term 1 over e to the a to the 5th will go to 0. 1 over infinity goes to 0. And so we have -1/5 times -1 over e, which gives +1 over 5e. All right, so it doesn't really matter what this value is. Really, I'm mostly concerned with the fact that the integral is convergent. So the integral converges. And so if the integral converges, that tells me that the original series will also converge by the integral test. Problem number 26, we have the sum of 1 over 4 plus n squared. I'm going to compare this to the sum of 1 over n squared. So note, since the denominator became smaller for the series that I just created, the denominator is smaller by 4 units, the overall value is bigger than the original series. I also know that this comparative series that I just created is a convergent p-series. So since the bigger one of the two converges, we can then state that the smaller series of the two converges by the direct comparison test. All right, number 27, we have the sum of n cubed plus 2n squared plus 3n minus 5 divided by n to the power 6 plus 3. All right, so for this problem, again, I wish to compare to a series. I'm going to create a series, and the way I'm going to create the series is by just keeping the leading term in the numerator and the leading term in the denominator. So in other words, I'm going to compare to the sum of n cubed divided by n to the power 6. A simplification here says that that's just equal to the sum of 1 over n cubed. which I know is a convergent p-series. So I'm going to use the limit comparison test because it is a little bit hard to come up with an inequality for this problem. So I will find the limit as n goes to infinity of the n cubed plus 2n squared plus 3n minus 5 over n to the power 6 plus 3, entire quantity divided by 1 over n cubed. A first step here would be to get rid of the complex fraction, and we do that by bringing the denominator up, multiplying by the reciprocal. So we'll multiply by n cubed over 1. I'm going to distribute that n cubed into the remaining part of that numerator, so we will get the limit as n goes to infinity of n to the power 6 plus 2n to the 5 plus 3n to the 4th minus 5n cubed over n to the power 6 plus 3. So if we find the limit as n goes to infinity, since the degree of the top and the bottom are the same, this limit goes to the ratio of the leading coefficients, which is equal to 1. And so the limit comparison test says that if the limit is a finite number between 0 and infinity, that we have an outcome, and that outcome is that the two series that I compared in the first place will do the same thing. So therefore, my original series is convergent by the limit comparison test. Number 28, we have the sum as n goes from 2 to infinity of 5 divided by n times natural log of n. So for this problem, again, I'm going to use the integral test. I'm going to let f of x be equal to 5 divided by x times the natural log of x. Again, a quick graph or writing out a few terms is going to confirm that this function is positive, decreasing, and continuous, so I may proceed with the integral test. We will find the limit as a approaches infinity of the integral going from 2 to a of 5 over x times the natural log of x dx. Again, before I proceed with the limit and the bounds, let's just quickly see what happens with the indefinite integral, the integral of 5 over x times natural log of x dx. I will use u substitution to evaluate this integral. I will let u be equal to the natural log of x, and so that gives du equal to 1 over x dx. So a substitution here gives 5 times the integral of 1 over u du, which is equal to 5 times the natural log of the absolute value of u. And then when I back substitute, this is equal to 5 times the natural log evaluated at absolute value of natural log of x. So back to my problem. We're finding the limit as a approaches infinity of 5 times natural log of the absolute value of natural log of x, evaluated from 2 to a. I'm going to apply the fundamental theorem of calculus, so that means plug and top minus plug and bottom, and let's evaluate. If we let a approach infinity, natural log of a is equal to infinity, which gives natural log of infinity equal to infinity. So we have 5 times infinity minus the natural log of 2. Regardless of the value of natural log of 2, we see that this integral is going to diverge to infinity. Right? So since the integral diverges, we know that the original sum, the original series of 5 over n times natural log of n will diverge by the integral test.